tomorrow because I have no idea how long I will be. Um, I could be in a meeting for 15 minutes. I could be in a meeting for 2 hours. I have no idea. Part of me has a fun. It's only a small group, but part of me thinks it could be long. So take an extra day off. It's supposed to be nice tomorrow. Go enjoy the sun, unless you have other classes. Um, I think I went through and answered everything. Hopefully, this is my file. Um, that first file, I'm pretty sure I posted it. Let's hope I did. I thought I did that yesterday morning. Yeah, yesterday morning I put all of the answers to everything in there. Some are a little bit straightforward. Next week I'll probably see if anyone has any questions. Today I wanted to look at word problems, which are solving equations. Then we'll deal with the graphing bit next week. So we have these sort of exponential growth problems. We talked about them a little bit. This is exponential decay. This is a neat, nifty one. And then there's a logarithmic one. I may leave the third one till the end. For an exponential growth sort of problem, we have kind of that base kind of structure. This is our initial amount. That's B is our rate or how often it does whatever it does. X is our variable, and that's technically our horizontal stretch. So when we have a population question that's growing by a percent every year, it's 2% this year, and then it's the compound interest idea. Um, that's our A0. This is how we're going to find our rate. If it's growing by 2% a year, our B is going to be 1.02. So the first part, we can term this as population. Let's move that down a little bit. Population equals 12,468 times 1.02. It's every year, so it's just to the x. So we did these when we did exponential functions. So that's part one. Part two, what will the population be after 8 years? Well, x is, so this one is fairly straightforward. We put the exponent in. I don't know why I put an equal sign in there. We need a bracket. Handy dandy calculator. 1.02 to the power of 8 equals 12,468 times 1.171659. Da, 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 da. Multiply that by 12,468. After 8 years, you're going to have about 14,608 people. That's the easy one. That was the one that we did way back when. When is the population going to reach 20,000? So in that case, this is where we couldn't solve it before. One, come on, fingers. 12,468. Oh my gosh. Well, I can't do anything right away. I can get the exponential on its own by dividing. I don't know how many places. We get the exponential on its own. Now we have the skills. Log both sides. If we log both sides, well, sorry, the color's wrong. 1.604107. Well, now we use our rules of logs. I'm going to take that down in front. Whoops. X times the log of 1.02. He's down here stealing food. X equals. And I've done like a lot more writing. I'm going to log that number divided by 1.02 log 23.86 years. So there's the power of logs. You can solve for an exponential sort of equation. Stupid cord. If they make us do this again next year, I'm going to make them buy me a Wi-Fi or Bluetooth headset. This cord gets in the way. So that's the kind of um, the basic type of thing. We can use this to model. This would be radioactive decay. Amount equals initial X is hours. How long would it take to decay? Well, the half-life is every 12 hours. So our initial equation, well, we've got 50 grams of this radioactive goo. I'm going to change that to a decimal just because it's going to work out. Over 12 and a half. Every 12 hours, we lose part of this. Well, we want to know how long it's going to take to get to 23 grams. How long will it take? Well, how long would it take to get to 25 grams? So a half-life question, we start at 50. 12 and a half hours later, we would get 25 grams. 12 and a half hours later, we would have 12 and a half grams. Then 6 1/4, and so on. And each one of those is going to be a multiple of 12 and a half. X over 12.5, divide by 50, divide by 50. That's 0.46. So we do that bit. And we log both sides. Log of 0.46 equals log of 0.5 times x over 12 and a half. Exponent comes down. Most people are going to do this step next. 0.46 log divided by 0.5 log equals 1.120 1.12 over 12 and a half, and then we can multiply that up. And I move that up times 12 and a half. I don't know why I changed the color. Times 12.5 equals 14 hours. So that is a radioactive decay. Not that most people have to calculate them, but radioactivity is an important thing. These half-lives can be in terms of years. It takes carbon 12 is like the half-life is 4,400 years. So in this case, X is hours. But if I had carbon 12 and I had X over 4,400, well, it would be every 4,400 years. So we play with those in that sense. We could do this as a fraction of days. I'm going to do this one third because this one is two equations setting them equal. Paleontologists can estimate the size of a dinosaur from incomplete skeletal remains. For carnivorous dinosaur, relationship between the length s in meters of the skull and the body mass in kilograms is expressed by the following logarithmic equation. To the nearest hundredth of a centimeter, what is the skull length? So we're looking for s of a Tyrannosaurus rex and an estimated body mass of 5,500 kilograms. So this is m solved for s. It looks like we have two logarithms. That's all well and good. But when we're doing one of these questions, I have to know one of those two variables. In this case, we know what m is. We need to solve for s. 3.6022 times log of s equals log of 5,500 minus 3.44. So there's our first step. Log of 5,500, is that not just a number? 5,500 log 3.74 44. I can subtract that. 3 minus 3 is 0, 7 minus 4. Algebraically, divide by log s equals 0.3 divided by 3.6022. Log of s equals 0.0833. Well, how do we get rid of a log? We convert it to, this is base 10, 10 to the power of 0.0833 equals s, the skull length. So I'm going to take that number, and that's why we have this 10 to the power button. S equals 1.21 skull length in meters. What does that say? To the nearest centimeter. Meters. That's so that would be the kind of how we want to go about that sort of thing. We have all. It looks like it's going to be more complicated than it is. There's with logs. There's multiple different ways we can do some of these. We want one on their own. So get the log by itself, and then go from there. Now, the last one, two die-cast metal cars are bought at the same time, or two figurines or whatever. The first one costs $99.50 and was appreciated by 10% every 3 years. Car number one had an initial value of $99.50. It appreciated by 10%, 1.1 every X over 3. Car 2 had an initial value of $49.50, appreciated by 16% every 2 years. That zero is redundant. 1.16, 1.16. Determine how many years it takes for the cars to have equal value. So when we want an equal value, we have to set the equations. The value is y. So we've got to get some expression that gets x by itself. If the values are equal, y equals y. So now we have two exponential equations. So the kind of easy way, log everything. So I have the log of a product, log of 99.5, because it's a product, plus of 1.1 plus now that's gonna, yeah. Number number exponential. So I'm gonna put everything that's a number on one side. So I'm gonna subtract that. Log of 99.5 minus log of, that's going to be positive. I'm going to move that x over 2 minus, so we normally write it like this. That's a number. We can figure that out. I'm going to leave that alone. It's these two bits that are tricky. X times log of 1.16 divided by 2. X times log of 1.1 divided by 3. This side has a common factor of x. This side stays the same. You can convert that to a number, but this is just a little bit more elegant, leaving things. You get less rounding error. If I factor out an x of this, we have log of 1.16, a number, divided by 2 minus, taking x out of this, taking x out of that, log of 1.1 divided by 3. Well, how do I get x by itself? I divide. That's a number. Divided by there's your exact answer. Let's do the numerator. We'll pull up our handy dandy calculator. 99.5 log minus log 1.69461. Oops. Wait. Oh, I had to push equals. Sorry. 0.303218. That's 5 places. 6 places. That works. Same thing. 1.16 log divided by 2. Subtract bracket 1.1 log divided by 3 bracket gives us I did this all out yesterday, that's why I'm looking over there. Well, I know what the answer is. 0.0184314. So I want to divide those two numbers. I don't want to rewrite that one, so I'm going to go like that, flip it over, times 0.303218, 16.45 years. After 16 and a half years, both cars would have the same value. Can we check that if we want?
Mr. McKay,
Yeah,
how did you? Oh, wait, can you scroll down for a second?
sorry.
No, that's okay. I just routine. How did you get the like you went from log 99.5 and log 49.5, and then how did you? Was that just in the equation, like the log 1.16?
So,
1.1?
so this expression, like how do we go from here to there?
I think yeah.
So log of 49 and a half is just a number, right? So all I did was just do like my little move something. That minus that goes away. Log 99 and a half minus 49 and a half, and then I did the same thing. Like I just switched sides.
Okay.
So algebraically those go away, so I get that difference and then that difference. That makes sense now?
I think so. So you just bring one to each side, and
Yeah,
it eventually just cancels it out because there's two on each side.
yeah. It's kind of similar to like, I mean, a really simple analogy. X plus 3 equals 2x plus 4. Like that, this is a number, this has a variable. So Madame Hayes always used to say letters on one side, numbers on the other. I think she said letters. I think she says letters on the left, numbers on the right. But so minus 2x minus 2x. So those go away. Minus 3 minus 3. So negative x minus x. So negative, like it's that same idea that we've used for a while. So just to look and double check, I'm going to, are these going to work out if I put 16 and a half in for x exactly? Probably not, because there's all sorts of rounding error. Oh, I guess it was 16.45 divided by 3 is that 5 point, okay. Can I get that? 1.18. Oh, this is what I wanted to do. Use the calculator. I've got brackets, so why not use the brackets? 1.1 to the power of that gives that number. After 16.45 years, this one's going to be worth, let's change the color so we have it, 167.8. No, 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 no. 1.16 to the power of, open a bracket, 16.45 divided by 2 gives us that, times 49.5. 100, oh, well, that was better than 79, which, based on rounding error, is an acceptable amount. So those are some examples. Tomorrow, after we finish our meeting, or maybe this afternoon, I'll post a couple practice questions if you would like. This one here is more complicated than you probably would see or would have seen on a test or an exam, but it's just some people like to compare things. Could you plot a graph of this and find out what it goes? Plot a graph of this. What you're fundamentally doing is finding where the two lines intersect. That y equals y in grade 10 math, I think we called comparison when we did systems of linear equations. It's a way of finding a point of intersection. It doesn't matter what type of equations you're using, whether it's two linears, a linear and a quadratic and a quadratic that you would have done with Mrs. Parley last semester. You can do it with exponentials, you can do it with logs, you can do it with all sorts of fun things. So that's what I wanted to go through today. I think there's one question on the assignment that has, I think it's a log equation at the end. I'll post those, and that was all I had for today. So if there's no questions, go mow your lawn or something. Or enjoy the sun, relax, or work. I'm not sure. Have a good day, though, and we'll talk to you next week.
Thank you.
You're welcome.